Imagine trying to rebuild a beautifully intricate, shattered vase using only a flat list of its broken pieces. It sounds, honestly, incredibly daunting, right? Well, today, we're tackling a classic algorithmic puzzle that feels exactly like that. In this explainer, we're going to completely rebuild a complex binary tree from nothing but two flat arrays. It's the classic build binary tree from Preorder and Inorder Traversals problem, and it's a really fun one. So the mystery really starts right here with a super fundamental question. Why do we even need two arrays to do this? Like, why can't we just take a single traversal array and reconstruct our tree from that? It seems like it would save us a whole lot of trouble. Well, this perfectly illustrates why that simply doesn't work. If you take a single in-order array, say 2, 9, 5, 4, 3, 7, it doesn't give us one unique blueprint. Actually, it can map to wildly different, completely conflicting tree structures. Without a second array acting as an anchor or a reference point, we're literally just guessing at the true shape of the tree. Okay, to crack this case and completely eliminate the guesswork, here is our 6-step roadmap for today. We'll cover the two-array puzzle, locating the root node, mapping the subtrees, the recursive strategy, optimizations for efficiency, and finally, a complexity analysis. Let's dive right into section 1, the two-array puzzle. Let's establish the ground rules. First up, we really have to intimately understand our clues. Look at how these two traversal methods operate. A preorder traversal always processes the current root node first, then it dives into the left subtree and finally the right. An in-order traversal, on the other hand, goes all the way down to process the left subtree first, then handles the current node and ends with the right subtree. These completely contrasting behaviors, that's exactly the friction we need to solve this puzzle. Here are the exact inputs we're working with, along with one absolutely crucial constraint. Every single value in our tree is completely unique. This uniqueness is huge because it guarantees that when we search for a specific value, we won't run into any duplicates or ambiguity. It's a lifesaver. Moving on to step 2, let's hunt down our most important anchor, locating the root node. Because a preorder traversal processes the root before literally anything else, we have a massive immediate advantage. The very first number in our preorder array, which is 5 in this case, is undeniably our root node. There's no debate. That is our foundation, and we are going to build the entire rest of the tree around it. So, with our root node firmly in place, it's time for section 3, mapping the subtrees, to figure out what goes left and what goes right. Now, this right here, this is the ultimate aha moment of the whole algorithm. Finding that root value of 5 inside our in-order array definitively maps out all of our remaining nodes. Because of how in-order works, everything to the left of the 5, so the 2 and the 9, absolutely must exist in the left subtree, and everything to the right, the 4, 3, and 7, must exist in the right subtree. It creates this perfect geographic split. And the real takeaway here is that this division tells us exactly what to do next. If our split in-order subarray actually has values left in it, well, we actively build a subtree. But if we hit an empty subarray during this process, it simply means that specific child is null, just a dead end. Now, we know from reading our preorder array left to right that 9 is the very next node we have to create. But how exactly do we know where it attaches to our tree? And this perfectly highlights our dilemma. Is 9 a left child or a right child of 5? I mean, we can't just guess, right? This brings us to the need for a systematic, repeatable engine that places every single node with absolute 100% certainty. Let's move into our 4th step and actually build that exact engine using the incredible power of the recursive strategy. To drive this engine, we're going to use 2 pointers. We'll use a preorder index to consistently grab the very next node we need to build. And at the exact same time, we'll use an in-order index to find where that node splits the remaining array into new, smaller left and right subtrees. It's really just a simple 4-step loop. This is the heartbeat of our whole explainer today. We create the node, we increment to the next index, and then we recursively call this exact same logic for the newly defined left and right subtrees. It just systematically chips away at the arrays until the entire tree is fully built out. Okay, section 5. Our logical blueprint works flawlessly, but, a great engineer always sharpens their tools. Let's talk optimizations for efficiency. Here's the thing. Every single time we make one of those recursive calls, a naive approach extracts entirely new subarrays. It creates a brand new array every time. And that is a silent performance killer. So we have to ask, Is array slicing just too slow? Is there a better, faster way to define our boundaries? Absolutely, there is. Slicing arrays is a major inefficiency that literally takes O of n time for every single slice. But we can instantly squash that massive overhead down to O of 1 time just by tracking coordinate points instead of actively copying data over and over.
Look at how smooth this logic becomes. By just assigning simple left and right pointers, we structurally isolate our in-order subarrays. We're effectively defining the boundaries of our subtrees dynamically, on the fly, without ever creating new, expensive arrays in memory. It's such a clean workaround.
And wait, there's one more trick. To completely eliminate the O of n linear search required just to find our in-order index in the first place, we introduce our final, most powerful optimization, a HashMap. By mapping all the in-order values to their indices right up front, it's basically an indexing cheat code. It gives us instant O of 1 lookups for any value's exact position. Let's wrap this up in section 6 with our final complexity analysis. We've solved it, we've optimized it, so let's see our final grades. Thanks to those clever pointers and that instant HashMap trick, our overall time complexity is an incredibly elegant O of n. We only traverse each element once. Our space complexity is also O of n, and that's entirely due to the recursive call stack height and the memory needed to store our map. So we just took a confusing, flat pile of numbers and turned it into a beautifully optimized O of n tree builder. But seeing a transformation like this really leaves you wondering, what other naive algorithms are currently hiding in your own code paste right now, just waiting to be brilliantly optimized?